All right, so we're back. So, what are the dimensions for surface area? What dimension is length times length, right? So, length squared. And the unit is meters squared again. All right. I know this is pretty easy. This is all review. So I just want to make sure we're all on the same page. So bear with me if you feel I'm insulting your intelligence. It gets harder. Don't worry. All right. So let's talk about units. Why are units so important? Well, if there's no standardization in units, everyone will be talking about same thing with different values, and there'll be lots of confusion and argument. For example, in the old days, they would actually go to a town and ask them for, I would like 2 stones worth of barley. Now, one town can have like stone that has a mass of like, I don't know, 10 pounds. A different town can have stone that's a size maybe 5 pounds. So it's not standardized. Matter of fact, some old systems, they actually used boar's head. Yeah, I know. It's not, like sanitary, I guess. But what they would do is they would actually, chop off the head of a boar in the town, and they would use that boar's head's mass as a scale, and they would find an equivalent, like a stone or sack of like sand that's equivalent to the boar's head's mass, and then they would use that as one boar's head, and ew, right? So it's very important to actually have a standardization for units. Um, there are 3 major systems of units that we should be familiar with. Okay, the most important one is the SI system or System International. The System International was developed by a group of French scientists. They got together in Paris and they decided to standardize all the units. Okay, and they called it a metric system. Now we call it System International. Okay, metric system that we use is meters, kilograms, and seconds, or otherwise known as MKS system. Okay, and that's what all scientists use today. We in the United States use a British system, and ironically, even the British don't use British system. We're the only ones. And chemists like to use CGS system, otherwise known as centimeters, grams, and seconds. It's much smaller scale, and since chemistry they use a lot smaller scale than physics, they use CGS. All right. So in MKS or System International system, we have 7 fundamental units that we should know. Matter of fact, British system and CGS, we only know up to 6, and we're not quite sure about the 7th one yet. The first one is time. Time is measured in seconds, and that is pretty much standard for all systems. So for British system, we use seconds, and so is the CGS system, we use seconds. So that's something that we could all agree upon. And matter of fact, it's one of the most abstract concepts that all humans actually agree upon without fighting over anything. Mass. Mass is measured in kilograms for System International. Now, this one has prefix of kilo in front. Okay, kilo. All the other ones are just regular standard base units, but the mass is the only one with kilo in front. Okay? In British system, mass is measured in slugs. I don't think this is the same slug like you see like creeping out of this garden soil after a rain with the slime on it. This slug is slightly different. I think it has to do with like a gun or a cannon bullet, like when you have slug embedded in you. In CGS system, they use grams. So don't get these two confused, please. Okay. This one is grams. This one is kilograms. Length is measured in meters for the SI system, and meter is slightly more than a yard. Okay. And for British system, they use foot. And many believe this foot comes from King Charlemagne's foot. Okay. And length for CGS is measured in centimeters. And centimeters is very small, actually. It's about a diameter of a dime. And temperature wise, we measure things in Kelvin for SI and for CGS. However, for British system, we use Fahrenheit. Don't get confused with Kelvin and Celsius, okay? Kelvin is more scientific. Celsius is more of a human scale. Current. This is electric current, and that's measured in amperes by all three systems. Ampere was discovered before coulombs, which is actually the charge. So it's sort of like this is actually a derived unit rather than, we'll get back to that later. Amount of matter in an object is also measured by moles, okay? And this is again same for all three systems as well. And last but not least, luminous intensity. For SI unit, they use the brightness of an object as candela. It basically, each candela is equivalent of one candle. So I don't know about what's going on with British system and CGS. So candelas are coming more and more into mainstream because of the LCD panels and monitors, and they measure the brightness of the monitors and TV using candelas. But you could also see them using looms. How many looms? So that's kind of questionable. I don't know if that's really correct unit for British system or not. So if you want to check that out and find out some information about this, let me know. Okay, what we use for British system and CGS system for luminous intensity. All right, moving right along. How are these seconds defined? Well, in the olden days, they basically used time as a measure of the sun cycle relative to the Earth. When you observe the sun, it would rise from the east and sets to the west. Now, depending on which part of the earth you live, it behaved differently. But since most human history were written by Northern Hemisphere culture, we can actually observe the sun's behavior by placing reference points and then taking a look at where it sets and where it arises, and then have it as a marker so that we can actually plant crops or prepare for harvest or party, you know. So if sun sets between these two rocks, you actually start planting crops. When sun sets between these two rocks here, you start harvesting, you know. So they decide to observe the sun's behavior to figure out time. And if you observe it long enough, you could actually see that sometimes sun will go the wrong way. And as winter approaches, suns get shorter and shorter and shorter, and people were freaking out, you know. So they actually would mark that time, which is winter solstice, and that's when the sun sets at the same spot 3 times exactly at the same spot. And from that point on, it gets longer and longer and longer again until summer. So they decide to break the cycle of the sun into 365 days, and that 365-day cycle pretty much became 1 year for us. And they decide to break up that 365 each day into 24 equal time, which is also an hour. And they broke up that hour into minutes, and there's 60 minutes in an hour. And then they wanted to be more precise, and they broke up minutes into 60 seconds. But that's the old way. It's not quite scientific because it's different depending on what day it is in the cycle. So today, as far as we know it, it is defined to be number of vibrations measured in a cesium-133 atom. Yeah, I know. I'll write that down for you. So 1 second is same as, ready for this? Of a cesium so when the cesium atom vibrates 9,192,631,770 times, it is equal to 1 second. So imagine being the guy counting that and keeping that up, you know? Like 1, 2, 3, too late. 1, 2, 3, 4, too late. 9.2 billion vibrations in 1 second. So why do we need something this precise for 1 second? Well, supercomputing as well as GPS system. And since things are so far away, you're going to need something really precise in order to measure and pinpoint the location of where the GPS is on the surface of the earth. So when they triangulate, they need some serious precision in order to pinpoint to within 2 feet of the accuracy. All right, mass. Mass is the next thing. Mass, besides being an hour of torture for me every Sunday, is amount of matter that makes up an object. Okay, in the old SI system, they used a platinum iridium cylinder. It's about about this big, and all the French scientists got together and saying 1 kilogram, and they all said, "We okay, 1 kilogram," and that was it, you know. So it's about size. It's hard to describe. Yeah, if I had this material with me, I could have shown it to you, but Next time when we meet face to face, I will. Okay. It weighs about 2.2 pounds, just to give you an idea what a kilogram is. Okay. So it's a platinum iridium cylinder that weighs about 2.2 pounds. And they all decide to agree on it, saying, "Ah, okay, that's fine." You know. But today, now, and this is pretty recent too. Now, it is defined by Planck constant, okay, H, to be, ready for this, 6.6260715 times 10 to the negative 34th joule seconds. Is that a big number or a small number? Yeah, very, very small number, right? I mean, very, very small number. So you could see the precision in that. So there's a huge precision with the new kilogram mass. Okay. Length. Uh, Long time ago, I guess, during the SI development, they decide to call meter to be distance from the pole to pole, and they decide to divide it up into 10 million parts and say, 10 millionth of, North Pole to South Pole. I mean, there's no pole there in North Pole, and there's no South Pole. Like, I mean, who's going to be measuring that? Oh, there's no way, right? So they just estimated it, okay? So they call that a meter. And again, it's a platinum iridium bar that was inside a vacuum tube, and that's all like temperatures standard, and they all decide to say this is 1 meter, en meter, and they're like we, and then it was done. But now they define 1 meter to be the distance that light travels in a vacuum. So that's how they define 1 meter. So let's write that down. So 1 meter is a distance, okay, that light travels in a vacuum. Oops. In 300 millionth of a second. That's fast. I don't know how many of you actually take pictures with digital cameras, and if you take one of those professional cameras, if you want to like freeze like an action shot of somebody like dunking or something, you want it at least 1/500th of a second in order to freeze the person out in the air. If you take a picture of a water drops and you want to freeze the water drop into perfect sphere, you want to maybe at 1,000th of a second, and that's pretty fast as well. But this is 1/300 millionth of a second, so that's pretty fast. Okay, so to give you an idea how fast the light travels, speed of light, okay, is That's approximately 300 million meters per second. All right. To give you an idea how fast that is or how far that goes, if you were to shine, let's say, laser pointer to the moon, it would take approximately 1.5 seconds. No, I'm sorry, 2.5 seconds to reach from Earth to the moon. That's pretty far out there, actually. So when you saw that video of how far the moon is from Earth, our moon is pretty far away. Matter of fact, it is so far away that we should be able to put all the planets in our solar system between the Earth and the moon, and we'll still have room left over. That's how far our moon is away. Our nearest planet, Venus, if we were to shoot a laser pointer from Earth to Venus, it would take approximately 140 seconds to reach from Earth to Venus. So that's pretty far out. Okay. Let's play a Godonkin experiment. I only have 3 minutes left, so here. Let's say a light takes, right, 499 seconds to travel from our sun to Earth. How far is Earth from our sun? So when photon is released from the surface of the sun, that photon travels towards the Earth, and it's going to take approximately 500 seconds to reach our eyes. Let's figure out how far our Earth is from our sun. All right? Anybody, hey? All right. Since speed is equal to distance divided by time, if we were to solve for distance, our distance is equal to speed times time. So since speed is equal to, I'm just going to use 3.0 times 10 to the 8th meters per second. And if I multiply that by 499 seconds, notice what happens to the second. The seconds will cancel out. And it should give us 1.497 times 10 to the 11th meters. Now that's really far out. That's really, really far out. So tomorrow we will use this number and talk about how far that really is in human scale, an earthly scale. Okay? So for today, I am finished with the lessons. And thanks for joining me. I'll see you tomorrow after the A lunch. All right? Have a wonderful day, everybody.
Thank you.
All right. Take care.
Thank you. Thank you.
Tomorrow, I want to see your faces.